you had a nice day yesterday. Well, the first half of the day was with our first part of the European Ground Motion Service workshop. And now we continue today with the second day of the workshop. We had more than 400 attendees yesterday, and I think today we'll have more or less the same number. My name is Ivan Konakchiev. As I said yesterday, I will guide you during the second day also, as I did yesterday, through the whole workshop. I work in the European Commission in the Directorate General for Defense, Industry and Space in the Earth Observation Unit. And together with the other participants today, we'll continue on the different aspects of the ground motion service, the European Ground Motion Service using Copernicus. So yesterday, for those who didn't attend, or even for those who attended, the day yesterday focused mainly on the presentation, the ground motion service. We had two sessions. The first was with the keynote presenting the rationale behind the service, and the second session were with more information about the service itself, where we presented the planning, the technical aspects, different products, etc. Anyway, if someone missed some of the presentations yesterday or the whole day, don't worry. There is a link on your screen where you can see the recordings from yesterday, and soon we will upload also the presentations from yesterday and from today. So this event will be available even offline after we finish today. So today we continue with what we started yesterday, and we'll focus mainly on applications of the ground motion service today. We'll have two sessions. You have the agenda, so you see the first session will be more on national use cases and expectations. And then we'll have a second session, which will be more on the downstream applications and services. So we'll have different speakers. I will introduce them later on when we start the sessions. So you see there will be very interesting presentations today. And we'll have a coffee break as we did yesterday in the middle. So as I said, there will be no coffee. We're sorry for this. We had to do it in virtual. But you'll have the time to take a breath and be ready for the second session. Now, that's all from my side. I would like to give the floor to Henrik Anders from the European Environment Agency, who will present the key findings from yesterday. Henrik.
Good morning, and thank you, Ivan. Yes, my name is Henrik Steen Andersen. I'm from the European Environment Agency. Good morning to everybody who actually also attended the sessions yesterday, and good morning to all new participants. It's going to be a very interesting day today. Yesterday, we had a few polls. We tried to find out, to take the temperature in a way. And we had a few polls live during the sessions yesterday, and I will just mention a few of them because they are somewhat related to what we are going to hear today. So we stated, for example, that EGMS will foster general uptake and use of satellite ground motion data and products in Europe, and we scored a 4.6 out of 5. It means a lot, and it means also that hopefully the European Ground Motion Service will also trigger more interest in national services and downstream applications. We had, in fact, a specific statement concerning downstream applications. We said EGMS will facilitate the development of downstream applications, and we got a score of 4.3 out of 5 again. This is something we really hope to see in the future, that public institutions, commercial companies will build either directly or indirectly on products and services provided through the European Ground Motion Service. Then we had also a few specific questions concerning the uptake. What do we need to do in order to ensure actually that these data will be used? will be trusted. So we stated, for example, regional user meetings are necessary to ensure the uptake and use of EGMS products. And again, we scored 4.5 out of 5. So it's clear that there is a need to look not only at European level, but also try to focus on different regions. We may need to adopt different approaches when it comes to user uptake, information, user meetings, things like that. And definitely, and this is also this was also clarified yesterday. Definitely, we need to work very closely together with the national services. We will hear about 3 of them today. And it's clear that they have a lot of experience on how actually to disseminate, to visualize, to use and promote these products. And of course, we need to work with them and learn from them. That's very clear. And last one I would just like to mention is that we stated training events are necessary to ensure the uptake and use of EGMS products. There we had a score of 4.8 out of 5. And it's clear, I mean, we need to organize training events. Could be physical, I mean, live, it could be online, but we need to inform about the products. We need to inform about the quality, what they can be used for, and of course this will be part of the package that we are going to launch very soon. Concerning the planning, and some of you may have not have, I mean, who did not participate yesterday, may have missed this. So concerning the planning, and if you're eager to get your hands on the products, um, as you know, we have had a call for tenders. We received 2 offers. We are evaluating and completing the evaluation, in fact, finalizing the evaluation, in fact, as we speak. We hope, and of course there are some uncertainty connected to budget and things like that. You know that we are, I mean, sitting between 2 phases in a way. We have Copernicus 1.0 right now, and we will move into Copernicus 2.0 from January. And there are some uncertainties connected to the budget, but we expect right now that we can actually start late this year, early next year, and we will have a first product available towards the end of 2021. So that's the current planning. And of course, we will inform you when we know more about the details. But I'm sure that most of you would be very interested in seeing a pan-European product, and we hope to have it ready and available to you towards the end of 2021. I think that's all what I would like to say, apart from the fact, of course, that this is going to be very interesting. There's a lot of things going on already, and the European Ground Motion Service will, of course, build and cooperate with these different activities that are going on already. So have a really nice day today, and I hope we will get a lot of questions, and we will try to answer them after each session. Thank you and good morning.
Thank you, Henrik. I think it's time really to move to the essential of the workshop. So we will move to the first session of today, which is dedicated to some of the national and regional ground motion services that are currently operational in Europe, and of course their expectations from the GMS. So we have 4 speakers coming from National Geological Services and Academia. They will introduce you to the characteristics and the main features of the Norwegian or German and Italian ground motion services. Before I proceed with the presentations and presenting the speakers and giving the floor, I would like just to remind you that you have the possibility to ask questions in the interface. So you see there is a tab with questions there, so you can ask questions. We'll provide the answers. Just a short reminder: if you have a question that is specifically addressed to some of the speakers, please indicate it to whom you ask this question, because it will be easier for us after that also to ask directly. And also, if you ask a questions earlier, it will be better, because we saw yesterday that in the last 5 minutes we got a lot of questions, and for us it was very difficult to answer all of them. So if you ask a bit earlier, we'll have the time to proceed with questions and maybe even combine some of the questions if we cannot answer everything. So just bear this in mind. It helps also for the communication. I mean, it's a different way of communicating, but I think we can organize and try to answer all of your questions without leaving anyone without answer. So let's start then. We start first with Dr. John Dels from the Norwegian Geological Survey. So he will present the INSAR Norway, the Norwegian Ground Motion Service. So John, the floor is yours.
Thank you, Ivan and Henrik. You can go to the first slide. Okay, so yesterday we heard a lot about the European Ground Motion Service, and EGMS sprang out of the experience of several countries. And today I'd like to share the experience of Norway in building its service. And the first question I'd like to answer is, why did we build it? Next slide. Well, like EGMS, the Norwegian Ground Motion Service developed to meet user needs. And initially, these user needs were our own. Next slide. It's almost 20 years since we started experimenting with INSAR in Norway, using data from the European ERS-1 and 2 satellites. Click. Next slide. Or rather, that's good. Pilot studies were first carried out in northern Norway, where we were able to detect deformation in some natural slopes, as well as in infrastructure. Next slide. Such as hydropowers and dams. We also looked over the cities of Oslo and Trondheim. Never before had we been able to achieve such a synoptic view of deformation over large areas with millions of data points. Next slide. As the Geological Survey of Norway was responsible for landslide hazard mapping, we obtained all the available ERS data for most landslide-prone areas of Norway. This is in the western and northern parts, to perform regional studies. To the right, you see just one example of a large unstable slope discovered during this first study. The moving area, which you see in red and yellow, is about 1 kilometer long of broken up mountainside. It's at an elevation of between 1,000 and 1,200 meters, and it's slowly moving down towards the fjord, a few less than a centimeter per year. And we now have some monitoring systems in place. Next slide. Although we discovered many new landslides using this ERS data, it had its limitations. Satellites had already stopped producing usable data for INSAR by the end of 2000, and we had to rely on the archived data. And also in Norway, there were very few scenes acquired in the descending, or in other words, the southward-moving orbit from the satellite. And therefore, there was almost no coverage of eastward-facing slopes. Towards the end of 2008, we began to systematically task the RadarSat-2 satellite to acquire about 800 scenes per year over the most mountainous areas of Norway, as well as the major urban centers. We still had to wait about 3 years before we could do initial processing, because in Norway we have winters and snow about half of the year, so we were only able to achieve 5 to 7 snow-free scenes each year. This is one of the biggest challenges we face in the northern countries. Next slide. To attempt to mitigate the problem of winter measurements for high-risk sites, we did some experiments using the installation of corner reflectors. These provide a discrete network of good targets that are visible throughout the year. On the right, you see one of our earliest designs, along with a before and after satellite radar image showing where the points, the reflectors are visible. And I'll come back to these corner reflectors later in the talk. Next slide. So then the next question is, with building this service now, why did we decide to make it free and open? Next slide. So one of the most important aspects of INSAR technique is that it provides consistent ground motion data over wide areas. And while we were investigating specific areas, for example, a tunnel constructed in Oslo, we saw evidence of ground motion throughout the city. Next. The area around Oslo Central Station is built upon reclaimed land. There's a large amount of organic sediments. Next. The railroad station in Skøyen appears to be undergoing some deformation. Next. Some subsidence can be clearly related to the depth of bedrock. This neighborhood has a very large, very deep bedrock foundations far below. Next slide. And some areas, the deformation or subsidence can be related to the geology. In this case, the soil in this area is marine clays. As we had neither the mandate or the resources to contact all the relevant stakeholders, it was clear that this data would never be known to all its potential end users if it wasn't made public. Next slide. So while we were working with RADARSAT-2 data, it was already clear that the new Copernicus Sentinel satellites were on the way, and these would provide unprecedented free and open access to radar data over the entire country. This would be of great use to the Norwegian public authorities. The Norwegian Space Agency established a committee, including ourselves and NVA, who are responsible for landslide hazard management, as well as both the transport authorities, to determine the best strategy for using this data. The white paper, translated to Mapping and Monitoring of Landslide Hazard and Infrastructure by Use of Radar Satellites, was released in 2014, and it outlined the need for a national ground motion service, free and open to everyone, not just government users. As the agency with a long history of producing and using ground motion data, Geological Survey of Norway was chosen to lead the project. Next slide. So now I'll tell you a little bit more about what the Norwegian Ground Motion Service is. Next. The project officially began in the summer of 2016. By November 2018, we were able to officially launch the public interface of the first nationwide ground motion using the first nationwide ground motion dataset. We use about 4,000 Sentinel-1 satellite scenes each year, and using this, we produce ground motion data for over 3.8 billion locations in Norway. Currently, the data is updated annually. Next slide. We present the data in a browser interface with a fully 3D map behind it. Behind each data point, you can see a history of the displacement measurements. The full 3D interface is critical for us in a hilly country like Norway. As you can see in the example above, it's important to be able to understand the relationship between topography and the movements we see. The browser interface allows us to have a choice of background layers, either maps or photographs, as you see here. We can do address searches, zoom to GPS locations, and other analysis functions. Next slide. The Norwegian Ground Motion Service is funded by the Norwegian Space Agency, the Geological Survey, and the Norwegian Water and Energy Directorate. So the three of us are joint owners of the project. The analysis systems behind the service, as well as the map server and client, are being developed by Norse with support from PPO Labs. Next slide. So how do we go about going from these satellite scenes to the data that we have? Next slide. The Norwegian Meteorological Service operates a data access hub as part of Norway's national ground segment. Every night, we download all Sentinel-1 scenes that have been acquired over Norway to our high-performance computing cluster, which is sitting in Trondheim. These new scenes are then pre-processed and appended to existing stacks of data. And every fall, after the snow starts, we produce an updated ground motion data set. Next slide. At the end of 2018, we discontinued acquiring RADARSAT-2 data over Norway, as we now had over 2 years of overlap between the data sets. However, all the historic results that we produced for those 10 years of data are available within our same interface. Next slide. So who's using the interface? And this was very interesting for us to find out after we devoted all this energy to producing it. Next slide. On launch day, we had over 2,000 visitors because we had had a lot of good media coverage the day before. However, since then, traffic has been quite steady. Typically, we have between 100 and 150 users every day, and we see from the statistics that it's predominantly during office hours on weekdays. We don't require any registration to use the data, so we don't keep track of who exactly is using it. However, the traffic pattern suggests it's mostly professional users. The bulk of the traffic, when measured in kilobytes, is from within Norway. Next slide. And while most of this data traffic is from Norway, we do see a lot of international visitors as well. As the first completely free and open national service, we got a lot of attention, not just on Twitter, but also with detailed write-ups in various professional blogs. In this example, David Petley, who writes a blog for the American Geophysical Union on landslides, wrote a very good description of the data and how it could be used. Next slide. And we also were happy to see that ESA and other organizations noticed what we were doing. Next slide. I've talked a lot about landslides as a use case in Norway, and this shouldn't be surprising given the importance of this hazard. In addition to NGU and NVA, who are the national authorities responsible for mapping landslides, of course, the transport authorities, local municipalities, and citizens are all affected and interested in this data. The data from our service is not only used to identify landslide hazard, but within our operational risk and hazard assessment procedures, we're also concerned about long-term movement trends of these medium and high-risk sites once we've identified them. The map on the right shows the location of sites in Norway where we are currently measuring ground motion movement on them using various techniques over a long period of time, often visiting with helicopters and measuring using GPS, other times with in-situ instrumentation. And the number of these sites is increasing every year. Next slide. Earlier, I talked about the use of corner reflectors to provide targets for ground motion measurements. This is no longer an experimental method, but part of our operational program. At dozens of sites around Norway, networks of such reflectors have been installed to provide local movement information throughout the year. Next slide. And while the installation of such equipment is not always easy in the type of training that we have, once the reflectors are in place, they don't require any further maintenance, data transmission, or electricity. Next slide. In this example, which is from the shown in the previous slide, we see movement of 2 corner reflectors on an unstable slope since 2012. Initially, using RadarSat-2, we were able to obtain measurements every 24 days. Now, since the network is observed by several overlapping data sets from Sentinel-1, we can measure the movement every second day. The data for all of these corner reflector networks are produced fully automatically in our system several times each week. Next slide. Landslides are, of course, not the only concern in Norway. Our data is also used to monitor critical infrastructure, urban subsidence, and also other natural processes. On the right are just some of the examples. Reclaimed land in Trondheim in the harbor, which is sinking, subsidence along the highway in Oslo, town of Tønsberg, where many houses are built upon thick layers of clay. And in addition, later on this afternoon, we'll hear about use of ground motion data in downstream industries such as real estate services. Next slide. So what happens in Norway now that EGMS is coming? We've been very actively lobbying for the establishment of EGMS, and we've been participating in its definition. So what's in it for us? Next slide. Today, we provide nationwide ground motion data with annual updates. In addition, we supply, as I said earlier, data for all our corner reflectors into our national landslide monitoring system, where they're combined with other in-situ measurements. And of course, we provide access to our archive products. Next slide. With EGMS in the future providing annual updates for all of Europe, INSAR Norway will be able to devote more resources toward local problems. We will provide more frequent updates for many high-risk sites around the country. We'll also begin to process urban areas more frequently. We'll continue to support our landslide monitoring systems. We equip several new sites each year with corner reflectors, as they are much more cost-effective than helicopter visits to measure with GNSS positions. We're not planning to stop developing either. We've been developing new tools for our users to analyze the data. And in addition, we're already planning for the data from new missions such as NISAR and ROSE-L. These L-band missions will complement the data we get from Sentinel-1 as we have better coverage in partially forested areas. Next slide. So what can we recommend other countries and agencies to do now that EGMS is just around the corner? Next slide. The most important advice we have based on our own experience is to prepare now and prepare for a huge influx of data. As I showed earlier, the data that we had from RadarSat-2 covered only part of the country. When we initially released their full nationwide data set based on Sentinel-1, we had over 100 new landslides identified within the first month after launch of our service. Above is an example of one of these landslides, potential landslides in the northern Norway. This is a 50 million cubic meter block of rock, as you can see, about as high as the Eiffel Tower, which is slowly moving down towards the floor to fjord. Eventually it will collapse. It might be hundreds of years from now, but the tidal wave that it creates will hit the town across the other side of the fjord. These 100 landslides that we've identified would have otherwise taken years to find at the rate of our previous mapping. Next slide. And this pattern that we saw with landslides, of course, will not be unique. Similar patterns will be seen throughout Europe when EGMS data is first released. These are more examples from within Norway. At the top, we see a hydropower dam, which is being monitored. On the bottom, we see a mineral extraction industry examples with tailings ponds and tailing piles. And on the right, we see another example of transport infrastructure, in this case, a highway with some deformation. And many other phenomena around Europe will see the same pattern, where the initial influx of data from EGMS will reveal huge amounts of new information. Next slide. So to summarize, we're looking forward to EGMS. We think that EGMS will complement our national service while we continue to provide data that will supplement EGMS for our users. We'll continue to develop our service by developing new tools and data sets. And of course, all of these new developments will be continued to be free and open to all. Thank you very much.
Thank you, John. Very interesting. I think it's interesting, and other national services can really come to you and learn from your experience. I saw there were several questions. Apparently, it's created a lot of interest. We'll try to answer this at the very end, and maybe some of them can be answered also in written. We'll see how to organize it. I suggest now that we move, we just crossed the Baltic and we move to the next presentation, which is from Germany. So we have Andre Kalia from the Federal Institute of Geoscience and Natural Resources of Germany, who will speak about the German ground motion service. So Andre, the floor is yours. Thank you.
Thank you, Mr. Chairman. Welcome everybody to my presentation. We'll present you the implementation and use cases about the German ground motion service. Next slide, please. So this is my agenda. I will give some motivation why we build up the ground motion service in Germany, the implementation use cases, and give a conclusion. But before I start, I would like to highlight some of the milestones, because it has been quite a long way. And I think the EGMS workshop is very important. First of all, of course, the invention of the PSI technique by Ferretti et al. In 2000 makes it possible to detect this kind of slow deformations with high precision. And then the GMES Terra Firma project from 2003 had already had. John, please mute your microphone. Sorry. And one result of the Terra Firma project was the persistent scatter interferometric wide area product, which somehow extends the PSI technique from cities to rural areas with lower PS densities. So this was required to be able to process large areas and with high precision. However, of course, the precision decreases with distance. But what I've heard from the experts is that we are getting to 1 millimeter per year over 100 kilometers of distance. So this is from the methodological side. And then, of course, from the space segment side, ESA launched Sentinel-1A in 2014, April, and already September, very fast, it was operational with this unique mission design. So the 250 kilometer wide swath, the medium resolution, the high revisit time, and the mapping mission design, and not the science focus. And of course, the long-term mission design and the free, full, and open data policy. And then from the user side, in Germany, I want to mention the second National Copernicus Forum in 2012, where the user community requested a German-wide ground motion service. And then it was concept was built by us and then discussed in several forums and workshops. So, for example, the National Copernicus Forum in 2015, 17, and 18. And we also made almost every year since 2014 workshops here in Hanover. And then in 2016, there was a tender for the German-wide Sentinel-1 PSI processing, and German Aerospace Center and the Remote Sensing Technology Institute won the tender and was contracted for the processing. And the result visualized on top of a hill-shaded dam, you can see on the right-hand side of the slide. And we will publish a new tender soon. And of course, an important milestone for us in Germany was the 25th of November in 2019, where we put this data product online. Next slide, please. So I have put some maps here showing some of the motivation. What would we like to detect? What kind of processes causing surface deformation? So for subsidence and landslides, for example. So mining, soft soils, landslides, and subrosion. And if you look at the left map, the mining, you can see the gas and oil extraction sites in the northern part, sometimes 3 kilometers depth, and you can see a subsidence on the surface. So these are the blackish areas. And then you see also the soft soils and in the low-lying marsh soils, sometimes below sea level. So in the second map, in the black areas at the northwestern part of Germany. And there's a question, of course, regarding the rising sea level caused by climate change and the subsidence in coastal lowlands. And also a second question regarding the infrastructure maintenance in this area, where we try to support infrastructure maintenance of gas water pipelines at the intersection between the buildings and streets. And you see also the peat soils in the northern lowland and in the southern pass. And there's a question, how is the ground motion of peat soils related to the peat growth and the carbon dioxide sequestration, which is of course a good thing in times of climate change, and the peat loss due to dewatering causing compaction and oxidation and emitting greenhouse gases. And then, of course, landslides and in hilly areas and subrosion causing sinkholes. These two we have to face a challenge, which is the land cover causing temporal phase decorrelation. So we get something, but it's not perfect from my point of view. Next slide, please. So what we do when we get the data is, of course, some kind of verification. So some characteristics. We have 20 descending stacks from 5 Sentinel-1 tracks and 21 ascending stacks also from 5 Sentinel-1 tracks. And in total, we get about more than 140 million persistent Quechua from 6,700 Sentinel-1 acquisitions. And if I compare the velocity rates with in situ data from more than 200 continuous GNSS stations, and I plot the difference, then you can see it on the result on the lower left. So the range between the difference of GNSS and PSI is in the order of plus minus 2 millimeters using this data set. And you can see the distribution of the continuous GNSS stations on the map on the right. And if I'm saying we have 140 million PS, this is the total data set. But if I clip it to the boundary of Germany, then I have 100 million persistent scatterer coming from ascending and descending, which means point density for both data sets of 280 persistent scatterer per square kilometer for ascending and descending, and for one orbit it's 140 persistent scatterer per square kilometer. Next slide, please. But this is just one number, and it might be misleading because the distribution is very heterogeneous, depending mainly on the land cover. So you can see a persistent scatterer density map calculated on a 1 square kilometer grid, and the reddish colors shows areas with more than 1,000 persistent scatterer per square kilometer, up to 6,000, more than 6,000. So this is mainly highlighting the big cities like Berlin, Hamburg, Munich, and so on. And then you have the yellow colors with or orange colors with a few hundreds of persistent scatterers per square kilometers. And then the yellow colors with lower than 100 persistent scatterer per square kilometer. And you also see on the left-hand side that we have almost 20% of the area of Germany where we have no persistent scatterer. So vegetation or land cover, is causing this. And if we look a little bit more in detail, next slide, please. I calculated the persistent scatterer density for one stack. So the persistent scatterer points are plotted as black points on the lower left, and in the upper left you can see the Corina land cover map from 2018, and I just calculated the persistent scatterer density per land cover class, and this is the chart that you see on the right. And you could see like 3 main classes of or groups of persistent density with respect to the land cover. So you have the urban areas at the top with about up to 1,200 persistent scatter per square kilometer, and then a group of land cover classes with a medium persistent scatter density, and then the very low persistent scatter densities in the forests and so on. Okay, next slide, please. Okay, and then this was just some impressions about our verification workflow. And then, of course, after verification, we put it online, first time November last year, and we updated it just about a month ago. So you can now find the Sentinel-1 PSI data product from 2014 to 2019 for ascending and descending at full resolution. You can see the mean velocity, and after clicking on a point, you can see the time series, both in line of sight and of course some quality matrices like the temporal coherence and precision geometry stack ID, and so on. And you can choose from background maps like the orthophotos or topographic maps. Next slide, please. And we, of course, not only put the data online, but also we have some functionalities. So what is online now is a interactive visualization. So you can change the range of the color bar. You can download and you can do some queries, filtering after the velocity and the coherence, and you can see the time series plot. Next slide, please. And next one, please. Okay, so for example, for mining, if we plot the map of mineral resources on top of the PSI map, we can see that it very nicely fits. So almost every larger ground motion area, which you can see on the left-hand side, has an indication of the cause. So, for example, the lignite mining in the western part with the large subsidence area, or the natural gas areas in the northern lowlands, and so on and so forth. And we also will publish this thematic data online soon in our WebGIS. Next slide, please. So looking again at this large subsidence area in the western part of Germany. So we are located in the lower Rhine-Graben. So it's an extension structure with normal faulting in north-northwest, south-southeast trending. And we have the open pit mine where we have the lowering of the groundwater to be able to do the pit mining. And this lowering of the groundwater table causes a widespread, wide area subsidence. So this is, for example, 77 kilometers. And you see the ascending line of sight observation on the left picture, and in the right hand side you can see the descending. And after combination and doing the two-dimensional decomposition, we can estimate the vertical and the east-west velocities. Next slide, please. So on the left-hand side, you see the decomposed vertical velocity, and on the right-hand side, the east-west velocities. So meaning that reddish colors are referring to points moving towards the west, and bluish points moving towards the east. And a superposition with the tectonic faults shows that the eastern part of the subsidence is very clearly confined by the faults. So we get really a value adding here from my point of view. Next slide, please. Another example I would like to share is in the northern part of Germany, in the soft soil area. This is the city of Bremerhaven, where we have a compaction of young sediments in these coastal lowlands. And we have differential displacements between deeply founded buildings and adjacent areas like streets, and the intersection between these deeply founded buildings and the street level, there can be damages at gas water pipelines, for example. Next slide, please. And here are some photographs from Bremerhaven, where you can see an offset between the building and the street level. and some damages also and cracks at the buildings. Next slide, please. So I want to conclude. So we have updated our WebGIS. We have now ascending and descending line of sight velocities. We have interactive functions, and you can download the data. And we are publishing a web map service because it was requested by the users. And we are planning to do this in early 2021. And we want to update the product once a year. Thank you.
Thank you, Andrea. I think it was interesting to see another example of the nationwide of the service, and it was good also to see some concrete use cases which illustrate this. We'll be back probably with some questions at the very end, but now I suggest that we continue our travel to the south, and we cross the Alps this time to go to Italy. We'll have Dr. Federico Raspini from the Department of Earth Science of the University of Florence and Dr. Luca Guerrieri, who will present the current status of the operational regional service and of the future national service in Italy. So Federico, the floor is yours.
Good morning to everybody. My name is Federico Raspini from the University of Firenze. And before to start my joint presentation with Luca Guerrieri, let me thank all the organizers for their kind invitation to this workshop and for the opportunity to present the operational ground motion services that are active in Italy. Next, please. In Italy, there are 3 regions that are currently monitoring their territories with INSAR Sentinel. And the first region to implement this service was the Tuscany region in October 2016. Then the second one was the Valle d'Aosta region in January 2018, and finally the Veneto region in July 2019. All the services are based on satellite interferometry, taking advantage of the high revisiting time of Sentinel-1. Next, please. Different actors are involved in these operational services. There is a PSI provider which set up a systematic processing chain for the elaboration of a Sentinel-1 acquisition, and which is committed to continuously update the ground deformation data using all the available Sentinel acquisition. Then the University of Florence, my institution, which analyze and interpret the data deriving from this continuous processing, and which is committed to transform data into usable information for the end users. The end users themselves, I mean the regional authorities, whose support is fundamental for the validation phase for the exploitation of the data. And finally, also the Civil Protection Department was involved at the very beginning of the Tuscany project, giving his support for the definition of guidelines for the exploitation of the data. Next. The rationale, the idea behind these regional services is quite simple, and it's to make the transition from static historical satellite analysis based on the processing of archive images to more dynamic monitoring of ground deformation. In other words, the idea is to mark a transition between a one-shot delivery and a continuous streaming of information. Next. The three regions, the Tuscany, Veneto, and Valle d'Aosta region, where these services are active, are quite different from many point of view. Different geological setting, different physiography and morphology, different climatic conditions, and also different styles of deformation and geological hazard to be monitored. In Tuscany, we have more than 90,000 mapped landslides, 50% of them classified as active. We have several major cities affected by land subsidence, and we have a wide area in the central part of the region which is interested by the exploitation of the geothermal resource. Next. Veneto is another big region in Italy where many subsidence areas can be spotted in a wide plain, and with an alpine sector in the northern part of the region, which is largely affected by landslide. Next. Finally, the Valle d'Aosta region has a typical alpine environment, alpine landscape, with narrow valleys, extensive snow cover, which make the scenario very challenging from the interferometric point of view. And the region is mainly affected by large deep-seated landslide. Next. The availability of INSAR processing for the three regions allowed us to carry out two main different activities. APS mapping, that is a quite ordinary activity that is performed analyzing ground deformation map, and which is devoted to detect and map moving areas, and the PS monitoring, which is the real added value of these services, because this PS monitoring is based on the analysis, the systematic analysis of a displacement time series, continuously updated with the last available Sentinel acquisition, and this analysis of time series allowed to identify anomalous movement. Next, please. Before talking a few words about PS monitoring, just a quick overview of the PS coverage for the three regions, starting from the Tuscany region with the ascending orbit on the left side of the screen, and the descending on the right side of the screen. Next. Sentinel coverage for the Valle d'Aosta region, also in this case ascending and descending. Next. And finally, the Sentinel coverage for the Veneto region, also in this case ascending and descending. As I said before, these maps are very useful to spot unstable area, but actually they have a limit that is they provide a static picture of the ground deformation pattern at a certain moment that is represented by the last acquisition covered by the archive that has been processed. So the idea is, as I said, is to set up continuous monitoring, implementing a monitoring plan that is based on the continuous processing of Sentinel images as far as they are available for the area of interest. Next. Following each update, the time series of displacement for all the millions points that are retrieved for the three regions are analyzed in order to identify those points that exhibit an anomalous movement. What does it mean? It means that we are looking for those points that exhibit a behavior in the last part of the time series that is not consistent with the kinematic behavior that is expected just analyzing the previous part of the time series. In particular, we are looking for those points exhibiting acceleration. Next. The anomalous points are analyzed one by one, update by update, and the information on the most interesting anomalous points affecting element at risk are delivered every 12 days to the regional authorities in the form of monitoring bulletins or in the form of short report. And these bulletins contain the information of the areas that, that have the necessity of further analysis. Next. Analysis that are in the form of joint field survey that is performed together with regional authorities and local municipalities. Further analysis that can include, for instance, boreholes to support the reconstruction of a detailed geological profile, installation of corner reflectors to increase the density of points, leveling campaign to validate INSAR data, as it happens in this particular subsiding area in central Tuscany. Or next slide, please. Or analysis that can include borehole, track meters, as it is happening for this particular landslide system in the northern part of Tuscany, landslide system that is affecting a small remote village along the Apennines. Next. Interesting acceleration trends have been identified also in the Veneto region, for instance, for the area of the Lamosano landslide, which experienced an acceleration during last winter. Next. And also in the Valle d'Aosta region, and this is the case of the Bosmatto landslide, a large and well-studied landslide in the Valle d'Aosta, which experienced a small acceleration during 2018. Next. As I said before, these activities led to the definition of guidelines, protocols, procedures that include precise timing and precise scheduling of the activities that each actor involved in these operational systems should accomplish, starting from the availability of the new Sentinel-1 acquisition until the release of the report following the joint field survey between University of Florence, local municipality, and the regional authorities. Next. Finally, I would like just to mention that another project is currently ongoing in Italy, leveraging on the Sentinel-1 coverage created by the remote sensing group of the National Research Council. And the purpose of this project is to map and classify the moving areas at a national scale, considering that using this coverage, many deformation signals can be retrieved, from subsidence to landslide to seismic and volcanic deformation. And that's all what I want to say in this presentation. And This is the current status of the operational services in Italy. And I would like to leave the floor to my colleague Luca Guerrieri from ISPRA, who will talk about what is coming, what is next. Thank you.
Thank you, Federico. I wait for my presentation. In the meanwhile, I present myself. My name is Luca Guerrieri. I'm from Italy, the ISPRA, that includes the Italian Geological Survey. And I have the task to show you what is available at national level and towards the development of the ground motion service at national scale. Federico has just shown what is available and operational in 3 regions, and examples of application to several type of mapping and monitoring. Now I have to increase the scale to the national level and to show you what has been done in the past, what is ongoing towards the development of this national ground motion service. First, I have to mention that in the past, since early 2000s, in Italy started a project of mapping, PS mapping, prepared by the Ministry of Environment. It was called Piano Straordinario di Rilevamento, and it was based on previous mission, Sembisat, and then updated also with the Cosmos Skynet mission provided by ASI, the Italian agency, space agency. Then on the right, the other example of a national national map prepared for civil protection purposes. Next. This is another example that was shown right now by Federico. Another example based on Sentinel-1, prepared CPNR using an algorithm, but again, it is here you see the comparison of 2 different images showing the deformation areas. In this is very interesting because you see that only the area affected by the earthquake, big earthquake that occurred in Italy in 2016 was clearly showing a deformation, a part that was uplifting and a part that was lowering. Next. As I said, the National Ground Motion Service does not exist, but the actions, the effort to improve, to prepare it has started since some years. I have to say that this service, the ground motion service, will be one of the 8 core services implemented within the Mirror Copernicus program. That is a big program funded in the frame of the Space Economy National Plan. So there is a big investment done by the Italian government focused on the development of these operational services in different topics, as you see, coastal monitoring, air quality, land cover, etc. But ground motion was identified as one of the 8 priority core services. Next. Our methodology started from the user requirements collections, because we strongly believe that this kind of service must be based on user needs, and the user can play a role and contribute in the identification of what are the suitable data sources and what kind of service are needed, so to requirements for the services, and also to say what kind of added value service are needed to allow also to not experts to use this kind of data. It is very important, especially to provide to people that is every day working in monitoring ground instability, to have a tool to easily be understandable and usable, and he has to know exactly what are what this datum can say and what are the sentences. So, and the users can, of course, contribute also in the validation. So, next. So, in this effort, at first we identified what are the main community of users that are can contribute to the development of ground motion service. I'm here to represent what the work was done within the system of geological surveys, national surveys. I work in the national survey, but this work was done together with the regional geological surveys. But of course, there are many actors that are interested within the civil protection system, within the Ministry for Civil Infrastructures and Transportation, and cultural heritage and tourism. Next. So, in concrete, our effort was started in 2016. We start to collect user requirements through joint meetings and discussion, and we collected 4 questions focusing on the user needs. And we had also a meeting with the EEA when they started for the development of EGMS. So the dialogue was constant together with from one side and to pan-European ground motion level other side to develop something that must be, let's say, in the middle. Next. So, as you see, as you know very well, most of the focus of this kind of services are mainly to monitoring low-velocity landslide accidents, natural and human-induced. But in Italy, we have a lot of stability caused by different geohazards. We have active tectonics and seismic risk. We have volcanism. We have glacial and periglacial dynamics. We have sinkholes that are big holes that collapse, and it is important to have a local monitoring on these unstable areas, trying to prevent the collapse, or in a case mitigate the effects of this ground deformation. And also some activities like storage, gas and oil extraction, and geothermal activity, something that is related to human activities but can induce some deformation of the ground. Next. Of course, we put the focus also on specific environment or areas where there is something that is critical. For example, the urban environment, the linear infrastructures, the cultural heritage, and just sites, yes, and some critical structural works that are strategic, and so that we permit any collapse of them. Next. I've also identified what are in our actually with the data input, of course, and as you knew, the Sentinel-1 at first in the CN, but also Cosmos Skymed that has some particular additional contribute, especially in the local scale, and the SAOCOM in the L band. And also the need to integrate data from previous missions. This is very important. On the other side, need to use a reference point, to use GPS data, GNSS networks, etc., to have a data that is calibrated and not more realistic, to have a sort of measure in the brackets, of course, of the deformation. Next. So users have defined after this effort these 4 scenarios. Of course, this is a sort of wish list. We don't expect that everything can be done, but we have identified these scenarios to say to the industry that has to work on it what are our expectations. So we see something that is regular monitoring and more or less what was called the PS mapping. Site-specific monitoring on specific areas, or let's say a landslide that is known to be unstable, or an alert service that is can be activated on demand with a specific focus and a very frequent revisit time. And also some use cases where we can use the maximum the maximum power of the monitoring. Next. Okay, this is the result of the list of products that have been defined in using in real time and in the further time. So near real time, we have products in the level 1 and in the level 2 for landslide and subsidence, for volcanic area crisis, and for seismic events. Of course, in the real time, we need some products that are useful to manage the emergency. And the difference between level 1 and level 2 is that level 2 has the velocity maps are calibrated with reference geodetic networks. And for seismic events, level 1 is for seismic programs, while level 2 are the 3D models and real-time monitoring and mapping of secondary effects. Next. So this is the list of products in the further time. Again, in a wide area, sort of PS mapping, level 1 and level 2, but in the further time, so with the goal to update the user maps and not a real monitoring. But the same, of course, can be done for ground motion monitoring of volcanic risk and seismic risk. Okay, next. So, in a glance, what is the added value of this national ground motion survey that we are going to implement? At first, we are going to develop a continuous and updating service dynamic. So with frequent revisit time and using both the further time to near real time. We have also the option to activate on-demand service. That is very important especially when the analysis alert. The option to use band, so CL and X band. What is important is also to use to have a full implementation with previous historical time series. So using past missions, we have an archive, and we must to compare this with what is monitoring now. And also to validate and calibrate with in data, we have seen level 2 products using taking into account NSS data. And of course, it's very important to have in this infrastructure available geological database that allows the users in the interpretation of this PS velocity data. Because we don't need only a red point or a green point, but we need a layer where we have the maps instability that allow to identify what kind of deformation we are monitoring. And the last is also very important to the possibility to develop services with added value, to customize the service really on the user need and to allow to also a not expert user to properly use this information for their daily work. Yes, next. I think this is the last one. Okay, thanks a lot, and I finish and I give the floor to Ivan.
Thank you, Luca. Thank you, Luca and Federico for this presentation. So I'm going quickly because we are running a little bit of time and we have a lot of questions. So I'm turning now to Henrik for the questions. What I would suggest, Henrik, is that maybe we can probably take 15 minutes for questions, try to address the most important one, and then we can try also to answer some in writing later on if possible, and then we'll stop at 11 o'clock for a short break, shorter than foreseen, let's say 10 minutes, and we continue if it's okay.
Okay, thanks, Ivan. Yeah, we have a number of interesting questions. What I'm going to do is to address at least some of the top rated questions, and I will pass on the microphone to each of the national services so they will have a chance to answer, because I guess these questions are quite general in a way. So the first one is really about, do you reprocess the full time series once a new Sentinel-1 epoch is ingested? I think that would be interesting for the National Ground Motion Services to answer. So let's start with John, please.
Okay, the simple answer is yes at this point, but keep in mind that when I say reprocessing, it's only the final step of the processing. It's only the deformation analysis. We continuously do pre-processing throughout the year, basically every night as new data is acquired. One of the reasons for this is that so far the time series isn't so long. It's only about 5 years long. And also we have an issue in Norway with this seasonal snow, so that we have to be a little bit careful with the processing. But we are moving towards a fully automated system in the future, where also the final step, the deformation analysis, is done automatically and continuously.
Thank you, John. Andre, would you like to add something?
No, thank you.
Okay, and I don't know, Federico or Luca?
No, it's okay.
No, it's okay. It's okay.
We will then move to the next question. As far as I understand it, it has to do with validation in a way. So how do you, it's actually addressed to Andre, but I would like to, all of you to consider this. How do you ensure that PS vertical velocity originate from the GNSS station? In other words, that you are comparing the same movement. So I don't know if we should start with Andre.
I can give a comment on that. I think it's a very good question, and the comparison I showed you with the 200 plus GNSS stations, it was just comparing the velocity of the GNSS antenna with the PSs in the surroundings, and using the median of the PSs in the surroundings. But there's a lot of initiatives, for example, from the federal geodetic agencies and also from companies who are building these co-located GNSS corner reflector sites nearby. And this would be, of course, much better to compare really the phase center of the GNSS with the INSAR. But we're using every type of in situ data that we get. I must not show you, but also leveling data and so on and so forth.
Okay, thank you, Andre. Luca, Federico, would you like to add something?
It's Federico. No, I don't have anything else to add with respect to what Andre just said. Also, in our case, we use not only GNSS station to validate the data, the INSAR data, but also leveling, as I rapidly show in one of my slides. And that's the point. All kind of in situ data are used for a reliable validation. Thank you.
Thank you, Federico. John, would you like to add something?
I think I understand the question being that this was to do with Andre in Germany actually combining the INSAR data with the GNSS signals and producing this level 2B type of data rather than a validation. We're not using that process at this point. We do use permanent GPS for validating in many cases, in which case it's just a physical question of checking that you are actually measuring the same block that's moving. But I understand the question as being to do with the integration of the data sets.
Okay, thanks, John. And now that you have the floor, in fact, could you maybe comment the next question? How long would it take for data from a newly installed corner reflector to make its way into your product? I mean, so because probably it will be more like identical to what we are going to see from the European Ground Motion Service. So could you provide a quick comment to that question?
Well, a couple of things. First of all, when we're using our corner reflector networks there to measure local deformation in high to medium risk sites. So it's very important for us to be doing a local calculation there where we have one corner reflector that's a stable reference point, and we're measuring only the differential movement between the corner reflectors. So this is a different use case scenario where you would simply put a corner reflector out somewhere and hope that it shows up in a product like EGMS or a national service. So we're using it in a different context. If you were to simply install a corner reflector network, corner reflector somewhere, it would of course eventually show up in EGMS or equivalent product, but it would be like a new building being built. It would not simply show up immediately. It would show up immediately in the satellite images, not in the final product. That would depend on the update strategy of the processing. But my suggestion is, if you have an area where you don't think you're going to get data now, go ahead and put a corner reflector up now, because the sooner you get it up, the sooner, the more data you will have eventually.
Thanks, John. I think we can move to the next one, which is also, it's addressed to Andre, in fact, but I think it's relevant for all national services. So the question is, are you employing the same PSI technique throughout the whole country? So let's start with Andre.
Yeah, the fast answer is yes. We are using the same technique, the wide area product technique. Yeah, to reduce the error propagation by distance, and yeah, then analyzing the residues in the overlap areas, doing bundle block adjustment to minimize the residue, and then calibrating. So the answer is yes, the same technique.
And I don't know, Federico or Luca, would you like to add something?
Hi, it's Federico. Yes, the answer is also in my case, yes, we use the same PSI technique for the 3 regional services.
Yes, also for the national level also is still going to be done, but it is our goal to have only one.
Thanks, and John?
Yes, we use PSI consistently with the Sentinel-1 data over the country. In the past, with RadarSat-2, we have used SBAS technique, but given the new satellite and with the way that Sentinel-1 is working, we have found that SBAS does not provide the same results. PSI gives us a much higher PS density.
Thanks. I think I will actually, before we end this session, I will move a little bit down the list, and there's a question concerning the uptake. So let me just see where it is. Based on your experience, what is the best way to reach users of these national ground motion services, industry administration planners, to drive the creation of national service? So I think let's start with Federico or Luca. This is a less technical question, but it's an important question, I think.
Yes, we try to start very early in the involvement of the users, and our effort started very early in involving and identify what are the different users. So geological surveys as well are the primary users, but not only. Now we take some time. Now we are ready, but I have to say that it was a big effort. But we are now sure that the service will be useful to who really need it.
Thank you.
Well, I confirm that the best way to uptake different users is to understand which are their expectation, which are their requirements. From our side, I have to say that most of our users are institutional users, I would say regional authorities or local municipality. And for them, another topical point is training and to make them aware or on which are the possibility and the limitation by using insert. So I would say training and awareness.
Thank you. Thank you. And John?
I would say that for the industry component, we didn't need to do very much at all because industry was waiting for this service in Norway, and the engineering industry jumped on the service from the first day and began to use it. What we have been really proactive with is working towards municipalities and land planners and so on. So we've had a series of workshops in regional workshops where neighboring municipalities can come and learn more about the survey service and how it works and how it's useful to them. This has been helped by quite a bit of good media reports of case examples where the data has been used in some cases in conflicts between various bodies. So the more the people become aware of it, the more it's used. And we get continuous questions, phone calls from various organizations asking for more information for it. So we think it's very positive. But certainly it's necessary to, at the beginning, to have workshops and try to reach out to the people who are most likely to use this.
Thank you, John. And Andre, would you like to comment as well?
Yeah, from our experience, the format of workshops and also pilot studies, case studies with administrations from state level, for example, geological agencies, also geodetic agency on state and federal level. In the format of pilot studies with really hands-on the data, we started with ERS and of course then with the Sentinel-1 PSI to really discuss and communicate the limitations and the possibilities of this technique is a good way.
Okay, thanks a lot. I think we are close. We are very close to 11, and I think what I will do is that some of the more specific questions I will copy into the WebEx chat, so speakers will have a chance to answer them in writing, and I will then make it available on Slido. So please be aware if I'm going to put some questions to you in the WebEx chat. So over to you, Ivan.
Yes, thank you, Henrik. Thank you. It's really a pity that we cannot answer all the questions, but I'm sure that we can answer them in writing because there are a lot, and people are really interested to ask. So I think what I would suggest now is that we stop for 10 minutes and we reconvene at 10 past 11. We continue with the next session. And we'll have also other time for questions later on. If we manage to have a bit of time, maybe we can come back to some of these questions, but I'm sure there will be also questions for the other speakers. So let's restart then at 10 past 11. Thank you. Good morning, Welcome back. So we proceed with the next and the last session for this workshop. Before we start, I just would like to remind you that there is a question in the polls where we invite you to share your experience. So it's an open text question. You can put some text. So this poll will stay active until the end of the session. So you have time to share your experience there. So the final session of this workshop, we will introduce to use some downstream applications derived from the data distributed by the national services or by the operational ground motion services that are existing, and some of them were already presented in the previous session. We'll have 4 speakers. So we'll start with Mr. Niels Broge from the GeoPartner Denmark, who will present how the INSAR brings tailored ground motion products to their customers. So Niels, I give the floor to you.
Okay. Can you hear me?
Yes, we hear you well. Yeah.
You hear me? Okay. Thank you, Ivan. And good morning, everyone. My name is Niels Broge, and my talk is given on behalf of my company, GeoPartner, and our partners in Geo, which is a Danish geotechnical engineering company. So I will talk about our INSAR project, which has a focus on developing downstream applications and services. So next slide, please. So what is INSAR? It's an abbreviation of integration of INSAR ground motion products with subsurface geotechnical models, alias INSAR. It's a project that we initiated this year, at the beginning of this year, and it runs over 2 years. So we are not even halfway through the project yet. The basis of the project is that it builds on national Sentinel-1 ground motion calculations that have been provided by the National Agency for Data Supply and Efficiency. And the long-term goal of the project is to establish a sustainable business for both our companies, and to migrate the platform to be able to feed on data from EGMS when the service is operational. Next slide, please. So we have a little animation movie presenting the project that I'd like to show now. Please go ahead and play the movie. There's supposed to be sound on this movie. Yes. Thank you. Can you still hear me? Please.
Yes, we can
Please
hear you.
present the next slide. Thank you. I'm sorry that you. I think the sound was off on the movie, but I will come back to the essentials of our project in the forthcoming slides. So, like I said, the service is based on data from the National Agency for Data Supply and Efficiency, who operates a free and open ground information service for Denmark. They have reprocessed data since 2018 and made yearly updates. And this national service has helped open up market opportunities, and it has been essential for us for implementing the INSOP initiative. This has all been done as part of the agency's objective to support and stimulate user uptake in the public and private sector, and also for the engagement with national users through workshops and so on. So please, next slide, please. So the objectives of the project are to calibrate ground motion relative products, line of sight data and 2D data, to generate a geological 3D model, to generate a 3D risk model based on the two first bullets, to generate value-added services together with customers, and finally to generate a roadmap for migrating the service to the EGMS service. Next slide, please. So this is a slide showing the MapGM data flow. The MapGM is a service related to bringing the satellite calculations to the users. To the left of the slide, we have the loss observations coming in from the national service at present and in the future from the EGMES. And we combine this data with the local benchmark data, which is then combined in the MapGM database, where we perform calibrations of the data and also make value-added products and generate statistics and so on. So the final products are then served through open geographical consortium standards like the well-known VMS and VFS services, but also we serve them as an application programming interface to query and download data sets, or to use for simple reporting and investigating purposes, or for coupling the ground motion data with other tabular data, such as it could be data on buildings, road, whatever, for business intelligence systems and analysis. So please, next slide. And so here is an example. If you look to the bottom of this slide, there's an example of a cross-section showing a model of the geological layers from GeoAtlas platform. And the top graph shows an output from MapGM showing vertical velocity based on historical satellite data from the national service based on Sentinel-1 data, and also a calculated velocity based on geology and compaction properties of the geological layers. And so the idea here is, of course, to be able to integrate these two data sources in order to assess cause and also especially to be able to predict risks in areas of interest using the combined systems and the combined data sets. Next slide, please. So the project has focused on three sectors of applications, if you will: climate adaptation, the utility of underground infrastructure, and building and construction. And it's all based on a report that was published by the agency back from 2007. Next slide, please. So here's an example of the 3D voxel model that is generated as part of the project. This is from the city of Aarhus, showing the city center and the harbor, which are characterized by a complex geology and soft soils. It's primarily based, not primarily, but partly based on harbor area infill. And there are many subsidence issues at play, especially in the central part of the city. So the processing flow is to generate the GeoAtlas 3D voxel model in order to identify areas prone to subsidence, not only in the XY coordinate, but also with the Z coordinate in place. And then integrate this 3D model with ground motion information, sorry, and to calibrate and validate the voxel model. And so the GeoAtlas 3D risk model can then be developed based on to quantify and predict the subsidence rates based on the combined information from the geology and the satellite-derived ground motion. Next slide, please. So here's another example for a customer in Thyborøn, the city of Thyborøn on the west coast of Denmark. What we see here is an image of loss data from the descending track. And there's a cross section there, and you see below the cross section which shows the geological layers of the area. And to the top right, we have used the ground motion data derived from the satellite to generate a future model of the elevation in the area. In other words, a future digital elevation model. And thus, using that as a basis for simulation studies, you can include the effect of ground motion in climate adaptation works. Next slide, please. And this is the last example, also from the city of Thyborøn. Here we have made a baseline measurement of all the wells and manholes in the city, in the town, and so knowing the exact depth and elevation of these manholes, we can calculate the slope of all the pipelines. And having this baseline established, we will now in the future for the city provide ground motion based surveying of the condition and the capacity of the pipeline system in the city. And with the combination of the geological model, we will also be able to assess and predict the risks. Next slide, please. So this is my last slide. Just to sum up the lessons we have learned so far is that it is imperative for small companies like us to enter into this market, that there is a national authority that will stimulate market uptake by providing a national ground motion calculation like the one that has been put forward by the Agency of Data Supply and Efficiency in Denmark. However, there could be other things that could further stimulate our work, and I listed them here. For instance, easy access to historic benchmark measurements. This is the basis for our calibration exercises, and sometimes these measurements are hard to come by. Possibly they're not even in a digital form, and so on. So this would be very useful for us. Also, incorporation of reference data from third-party and national databases. In other words, having a centralized database all references would be a help. And a best practice for collecting reference data, for instance, from radar reflectors, but especially from benchmark measurements, would be very useful as well. And finally, last but not least, transparency and roadmaps regarding national activities would certainly be very useful also, so that we can orient our market development and business development in the right direction. So, please, next slide, please. And this is my last slide. Simply to say, of course, we are very interested in collaboration and learning more about other activities like our own. And here is the contact information to me and my close colleague in Geo, Mes. Thank you for your attention.
Thank you, Niels. I think this interest is mutual. How you like to learn, but I think also people may be interested to learn from you. Thank you very much for this presentation. It was interesting. Unfortunately, we pushed the system to its extreme with the video, so it didn't work. But anyway, this video will be published after that on the website, so people can see it and hear it, I think, which is more important in this case because they saw it already. I'll move now to the next presentation, which is from Dr. Sebastian Caro from GAF, who will talk about the value-added services and how one can use ground motion core services to generate values. So, Sebastian, it's up to you.
Thanks a lot, Ivan. Can you hear me well?
Yes, we hear you.
Okay, thanks a lot. First of all, I would like to thank the Commission and the EA for organizing this really wonderful workshop. It's a great pleasure to participate and to listen to all that very good and nice presentations. So we have been asked to talk about a bit the commercial, let's say, services which we are providing or which can be provided along with or based on the core services which are operated by the public institutions. So it's, I think maybe my presentation will be able to answer as well some of the questions that have been raised yesterday concerning the commercial impact or competition of this public operated EGMS, European or national services. Next. I don't want to spend too much time here, but just that you know who we are. We are a GI and Earth observation based turnkey solution provider, approximately 250 people in Germany. What is important on this slide is, so especially for the INSAR domain, we are not only benefiting from our technical units, which are taking care, of course, about all this technical processing stuff, but as well from our thematic expertise, which is organized in, for example, our geological department, which is really needed to interpret the complex information which is derived from the core services. We are mainly following three INSAR-related business lines. So we are providing core services by ourselves as well. We are providing value-added services, and we're providing Zoom services based on commercial SAR sources like Cosmos Climate or TerraSAR or any upcoming missions. Next slide, please. The core services which we are relying on have already very well explained by the by the previous speakers. So we are relying on the already operational ground motion service of Germany. We will hopefully rely on the European ground motion service to be implemented in the coming months. And we are providing an own ground motion service type, which is more or less based on the technology which has been developed by DLR, which is really scientific sound and which we already have implemented in our private cloud at GAF. So, and we are now able to provide that core service type applications at a global scale based on Sentinel-1 data. Next, please. The value-added services or the lines of value-added services we have in mind are basically two types. One are really the value-added services, let's say, to support the release and user needs. So there's still a big gap between the information which is really provided by the core services, which quite a complex information, with huge databases, point clouds, which have to be aggregated, interpreted, decorrelated to be really to really feed the needs of the clients and really to be integrated in the business processes of our users. So this is one of the value-added services which really makes sense, at least from our point of view. And the next slide, please. And the other one is, let's say, what we call Zoom services. So I think we have already seen it in the previous presentation that if you rely on, let's say, commercial data sources, then you can multiply, of course, especially the point density. So if you have already clear indications that there is some critical movements, then you can really take a closer look with commercial SaaS systems, and this will provide or is providing, of course, more dense point clouds, and you can as well, let's say, adapt the geometry of acquisition and the frequency of the acquisition better to the phenomena you're observing. So this is the second part of the commercial services which we are already offering. Next, please. In the following slides, I would like to give you a bit of insight of two, let's say, public funded projects which we are involved in. The first one is, let's say, an application which is called Sumo for Rail. It's an ESA funded project, which is aiming for the integration of the products provided by the National Ground Motion Service into business monitoring processes of the German Railway Authority, and to manage risks along the logistic chain. Especially, we are looking for the detection of critical phenomena, the categorization of this phenomena, of course, including in situ data, and the interpretation and integration into existing business processes. So I think this is exactly reflecting the first type of value-added services, which I've briefly mentioned in beforehand, and we are at the moment in the midterm of this process, and we already found quite interesting, let's say, phenomena, and the German Federal Railway Authority is very interesting to follow on that, and so we are going to the second phase of the project in the next weeks. Next, please. Here you can see on the right side, André Kallia already explained it in detail. It's an overview of the German ground motion service, and you can see the study area where we are. We are in the western part of Germany, the Ruhr area, where we have a lot of mining activities, of course, and you can see on the left side of the slide the areas of interest. Of course, these are the railway tracks which you can see, and you see already briefly what we are doing. We are looking for activity areas. We are, let's say, decomposing the products coming from the German ground motion service in vertical and horizontal displacements to be able to better describe the existing phenomena. Next slide, please. The ground motion. So what you can see here is the ground motion along the rail tracks we already found. We are doing a separation of motion components and aggregation to detect the active deformation areas as a fundamental data source for the user. So this is more or less all what we are finding here is mining induced subsidence close to rail tracks, and a dominant vertical displacement is observable. Less tectonic movements in horizontal direction. Next slide, please. So what we are doing, and this is exactly the gap which has to be closed. We are aggregating the information. We are detecting and classifying the different ADAs, considering the horizontal and vertical displacement, considering geological, tectonic, and seismic reasonings. We are, of course, including a lot of, let's say, other source information. For example, digital terrain models, of course, to let's say, to work with the slope and aspects and to better explain the phenomena we are observing. And of course, we are working with geological maps, which gives us a strong indication of the reasoning of the deformation and the velocity which we are detecting. Next, please. Here you can see, for example, the information derived from the geological maps and giving us indication of the soil types. And so we can explain the phenomena we are observing. And we are calculating as well the slopes for the potential unstable areas to provide information of the risk and the railway tracks. And this is mainly the final information which is provided to the clients and integrated in the business processes. Next, please. This is another application which we are involved in. It's as well an ESA project. It's led by Aegeus, our mother company, but as well in an international consortium with Tre Altamira as well. And here we want to let's say, to progress towards an European level. So we are again focusing on railway networks and the integration of different processing techniques and data sources. So in this project, we're not doing only the value adding of the complex information provided by the core services together with in situ data, but we as well are providing Zoom services based on commercial data to really take a closer look at the observations we have found based on the core services. And the overall goal is, of course, to monitor critical infrastructures. And most important is always in our application to really reflect the varying user requirements and to add in situ data and other sources of information to the Earth observation-based core information. Next, please. These are the main use cases we will analyze in this project. So we are looking on the monitoring of soundproof walls, of bridges, of geologically induced movements, of ground motion due to groundwater fluctuations, slopes, and embankments monitoring. We're looking to phenomena caused by long-term monitoring of climate change, monitoring of slow moving points, and vegetation monitoring, which is as well an issue for railway tracks. Next slide, please. So what is our way forward? GAF is currently intensifying all application and service development efforts on a national, European, and global level based on this, let's say, INSA technologies, which we are involved in more than 10 years now. But we find that this implementation of the core services from the public authority especially, we are pretty sure about this will create a stable user basis. And this is really very important for us. And there is really enough space for commercial applications. Let's say, really to close the gap between that quite complex information which is provided by the core services towards the really user, or let's say the information which is really required by the users and by the business process of the users, which we want to close. And this will be done, of course, in the domains of civil engineering, infrastructure operations, geothermal energy, defense and intelligence, risk and insurance, oil and gas, and for the mining industry. So next slide, please. So this is basically has been my presentation. So I'm really, again, it's a pleasure to participate in this very, very beautiful workshop, and I'm open for further questions. Thank you.
Thank you, Sebastian. The pleasure is also ours. I see that you have a lot of experience, but also a lot of work in front of you.
Yes, exactly.
Okay, nice. So there will be some questions probably, but we'll put them at the end. So I suggest that we move now to the next presentation, which is from Mr. Sven Krak from EVC, who will present the use of the INSAR with real estate and insurance domain. So Sven, it's up to you.
Thank you. Good morning, everyone. Next slide, please. My focus in today's presentation will be on how we already have taken and used INSAR data and how this data can be used to monitor subsidence and possible consequences for the building stock in Norway. Next slide, please. In Norway, we have approximately 5.2 million registered buildings. They are again divided in subcategories. 3.2 million private homes, 1.7 million leisure homes, such as cabins, summer houses, etc. Around 64,000 public buildings like hospitals, schools, town halls, and around 38,000 larger buildings such as offices, apartment buildings, and such. Private homes stand for 87.5% of all buildings. And if you look at the map on the right-hand side, we will see how these buildings are spread around the country. The yellow color shows a plot of buildings, and the highest density of buildings is in the southeast, and it then follows the coastlines to the middle parts of Norway. In the northern parts, there are more scarce buildings. Next slide, please. We started the project using Sentinel-1 data, where we wanted to find out if INSAR data can be useful in terms of monitoring building health. We started to look at bursts from southeast of Norway, as shown in the map on the right. The area the burst covers consists of both highly populated areas, such as Oslo, and municipalities around Oslo, as well as very large municipalities, but with a widespread and small population. One factor we looked at to determine the viability of INSAR usage was the point density, which in this case means the number of points we were able to find per building on average. We found that for private homes, we got 1.5 points per building, while we got 12.5 points for public buildings. If we look at the coverage, which means buildings with points versus buildings with no points, we saw that around 38.4% of private homes and 68.4% of public buildings were covered. Most of the undetected buildings are smaller than 100 square meters. This is pretty expected since each swipe from the satellite covers pixels of 5 by 20 meters, which equals 100 square meters. However, as we heard yesterday from Dr. Michele Grossetto, the number of points is affected by the surroundings. For instance, in areas with a lot of vegetation close by, we found fewer points per building, while we found more points per building in highly populated areas with no or little vegetation close by. If we look at the subsidence per building per year, we found that 95% of the buildings had movement of from 0 to 10 millimeters a year. Around 4% of the buildings had subsidence movement of 10 to 30 millimeters per year, and 0.6% of the buildings had 30 to 90 millimeters per year, which is, of course, significant. These numbers are based on one satellite's descending run, so we might expect better numbers when using both satellites and their respective ascending and descending runs. Next slide, please. To be more precise on our findings, we will look more closely at two concrete examples which shows accuracy and strength using satellite data, both for measuring external factors as well as internal factors in a building. On the top right, you see Hadland High School with its neighboring areas. The school itself is covered in green dots, which means no or very little movement subsidence. However, the area in front of the building is covered with red dots, showing a subsidence of around 100 millimeters. This is also expected since it is in a marsh area. The school itself is partly built on rock and partly built on poles. The contractor in this case took the necessary precautions due to the fact they were building partly on marsh. If you look at the other buildings in the same area, we see a lot of blue and red dots. Blue means an increase, while red means subsidence. The building in the middle is a grocery store. Here we measure internal movements in the building of between 80 and 100 millimeters. And this means the building is partly twisted, which is, of course, not a good sign for the building owner, and they need to be aware of this. In the bottom of the same picture, we see another building with a lot of green dots. This is a hardware store. And it's interesting to see why is it that this building is not showing signs of subsidence when laying in the same troublesome areas as the rest of the buildings. The difference is that this building is built by the same contractor that built the high school. In other words, they are taken into consideration the ground conditions in the area they build. If we take a look at the picture at the bottom right, we see a 4-story building. This building is set up in recent years. Quite soon after people had moved in, they started to see large cracks, etc. in the apartments. The project owner were afraid that it was related to poor groundwork and started doing in situ measurements. These measurements showed only minimal motion on ground level, under 10 millimeters. It's the red arrows and dots that you see in the picture. We then used satellite data to do INSAR measurements of the same building. And we found internal movements of more than 40 millimeters, which was corresponding very well with internal damages in the apartments. And people had to move out from a few of the apartments while they were actually being fixed. So of course, this is very significant for the project owner. And it's also interesting for us to see that we are able to discover and detect movements in a building using satellite data when in situ measurements show no or very little movement. Next slide, please. What are the gains by using INSAR data to monitor buildings and building activity? The two different examples we have given shows that we are able to use INSAR data that may prevent possible damages by building accordingly to ground conditions, but also to follow up on possible internal and structural damages on a building. In the latter, it gives us the possibility to start necessary measures at an early stage. Our findings show that we have around 250,000 buildings with movement of more than 10 millimeters a year. Of these, around 30,000 buildings have movement between 30 and 90 millimeters a year. All of these buildings should, of course, be monitored so that it is possible to take early measures when needed. A simple estimation using remedial measures per building of 100,000 Norwegian crowns shows that cost of measures will be 25 billion Norwegian crowns, which is about 25 million euros. This is a conservative calculation if we are talking about structural damages, but it shows the enormous economical effect for the community as a whole. In Avicii, we have developed a product called Servicehefte Bolig, which is a service leaflet. This solution gives the property owner the possibility to document the health of the building over time. One of the data items which is very important for this is the subsidence data set. We show subsidence data associated with a building over time, which makes it possible to follow or detect unwanted movements in their building or in the surroundings, thereby providing security of their possible biggest investment in life. Next slide, please. How does it affect real estate and insurance that we are now able to use satellite data to see cause and effect? Next slide, please. For real estate, we are talking about the importance of status quo. As mentioned, for a property owner, the biggest investment of their lives is probably buying a house. Naturally, it is of utmost importance to maintain or even better increase the value of the investment. If sensory information like subsidence or other sensors run counter to the maintenance efforts, then it's likely that the property owner will not take part in the property increase, but rather risk a value decrease. Next slide, please. In our work developing Servicehefte Bolig, our partners from the insurance and real estate business, in particular the real estate appraisers, points out that documented stable buildings and properties are more attractive and secure investment objects. If you have two identical houses where one is showing signs of subsidence and one is not, then obviously the one showing no subsidence is more attractive in the market and will give a better price. Moreover, merely having the data makes a difference. And as we can see here from the CEO of one of the biggest appraisers in Norway says, fine-grained satellite data that can detect vertical motion in buildings is powerful. It enables preventive measures, early diagnostics of possible damages, and gives more security and less disputes when buying and selling. Next slide, please. How is the subsidence data best used, or how can we put the subsidence data to use? Early detection makes it possible to take early measures. This is important because you catch the anomaly before it has caused too much damage to the building. This is essential to keep the cost of improvement as low as possible. When analyzing an area during pre-construction studies, we can identify trouble areas. By associating the subsidence data with existing buildings, you get empirical data that helps you employ the right construction techniques for new buildings. Here we can refer to the area around Haldan High School, as shown earlier in the presentation. On the right-hand side, you see two articles showing examples that might have been avoided by early use of subsidence data. One is showing Refta Skole, which is a school that had to close because of weaknesses in the construction. The other one is a storage building that collapsed because of heavy snow on the roof. After the incident with the storage building, we checked the data that we had, and we saw that the subsidence data for this building showed more than 70 millimeters of subsidence in the center of the building. If the owner had known about this, he probably would have been more diligent in removing snow from the roof. Luckily, the building collapsed half an hour after people had gone home from work. Next slide, please. The insurance business is conservative and generally risk-averse. If they do not have large historical data sets, their actuaries have no way of calculating the risk for a particular insurance product. And historically, there has been little or no data on subsidence, which means that they do not cover damages caused by subsidence at present. However, the short-term gain is that it can be used to perform risk evaluation in general. In the long term, the insurance industry sees the possibility to provide insurance products and offer coverage, but it has to be both profitable and attractive products for them. Next slide, please. And then the question is, can this data be used in other areas? Next slide, please. As we have heard earlier today, it can be used to monitor a lot of different infrastructure. I would like to point out, though, that when it comes to buildings, it is important to be able to draw upon data sets from different domains altogether. For example, if we can relate subsidence data over time to new building activity, it is possible to determine cause and effect, which by the way is important for the insurance industry. As an example, we have seen cases where a shopping mall had to close down due to road construction activities 300 meters away that caused ground instability. It goes without saying that economical consequences was enormous for the mall. It is not only related to fixing the building, but also the fact that during the period where the mall was closed, the customer habits changed, and it's very hard to change it back. And none of this is covered by insurance. We have also seen cases where new building activity in highly populated areas has caused long-term damages to existing buildings. Why is it so? New buildings are constructed using other techniques than in the past and can cause changes in the groundwater level that may cause hazard to the older building's foundation. Historically, many buildings were built using wooden poles. New activity may expose these poles to erosion, which again may cause severe damage to construction. The only part of discoveries that we have seen using this data. And I think I also need to clarify a little bit when it comes to the economical effect. I said 25 million euros. It's 2.5 billion euros, which is the effect of the damage that we have found so far. Thank you very much.
Thank you, Svein. It was interesting to learn also from your experience. I think for me, what was interesting also to see is this difference between the in situ and the satellite-based measurements on the ground motion. So it's an interesting point. I suggest that we move to the last presentation of the workshop, which will be done by Mr. Jeff Sawyer from the European Association of Remote Sensing Companies, who will talk about the value of the ground motion services. So Jeff, it's up to you.
Thank you very much. Great. Welcome everybody. I'm going to talk today not so much about ERSC and the commercial sector. I'll make some references at the end, but I want to talk about the value of ground motion services based on work we've been doing with ESA and the Commission. So next slide, please. So firstly, let me tell you about the methodology of what we're doing, and then I use that to show some examples particularly relevant to the ground motion service. So on behalf of ESA and the Commission, we've been looking at the value created through the use of Sentinel satellites. So our approach is to take a single product, single service using Sentinel data and look at the impact that has right along a value chain. So from the service provider through what we call a primary user, through to society and a local community. We developed a portfolio of cases and with a mix of different data types, countries, which I'll show in a moment, but really today I'm focusing on INSAR. One point to make clear is that it is primordial that the service is in operational through what we call the primary user. So we're really looking at situations where the use of the service or product has become embedded in the operations of a user. Next slide, please. So this is just to give you a picture of the types of cases that we've looked at. I won't go through these. You can find them on the website. But we have full cases where we go a detailed analysis, and short cases, which is more about the story. In fact, all of this is about telling the story of the use of satellite data. Next slide, please. So SEBS, so the Sentinel Benefit Study, takes this value chain approach, and while the early studies focus primarily on the economic benefits, a number of the case studies that we did show that much of the value generated is not economic in nature. So our goal now is very much to move beyond just the economic analysis and to look at the full range of benefits. So we're looking at different dimensions of the service in a holistic way to look at the quantitative and qualitative benefits. Next slide, please. And this came out from some of the cases that we looked at, where in discussion with the users, it became clear that there was more to the story than just an economic value. So the two on the left in Ireland and Belgium both enabled the creation of a local community. So in Ireland, the local emergency services could work better together, having a common operating picture. And in Belgium, different administrations and different stakeholders came together, knowing that, or with the benefit of a national picture of potato growing. In Sweden, there are 300,000 families that own woodland. They're all acting individually, but at a national level, the goal is to increase the value of the timber and the value of the resource as a national asset. And in Greenland, knowing that when the ice is forming, in order to serve very remote communities, helps support what is a very remote and distributed population. So these two have very much strategic benefits. And then in Norway, which we'll come back to in a moment, better regulation is possible due to the fact that you can measure and know that you can measure the ground movement. So next slide, please. So this gives us 6 different dimensions of value that we've defined. The economic, of course, I won't go into the details. The environmental value, the regulatory value, so how you can produce better regulation or how you can monitor regulation better, as indeed we're seeing with the reforms to the CAP. Innovation and entrepreneurship, so how it affects industry, how it's supporting innovation in organizations. Contribution to research, so the service or the product has a dimension where it's helping researchers improve services or improve research in completely different areas, it can be. And then the societal impacts, where maybe better health or better use of resources in the roads example, less closure, less time that roads are closed. Next slide, please. So these 6 dimensions are taken across the whole value chain that we look at, and we will see that in just a moment. So there are 3 cases that we've so far completed which deal with INSAR and ground motion. We have a further one, but it's awaiting approval from the primary user for publication. So let me focus on these 3 cases. The first one is about water abstraction in Spain. The second one is about monitoring the pipeline infrastructure in the Netherlands. And the third, coming back to the case that we've heard several times today, ground motion in Norway, with our focus very much on the roads management. Next slide, please. So firstly, aquifer monitoring in Spain. Here, what's going on here? The Secure River Basin Management Authority, CHS, is abstracting water from underground aquifers in order to service the local community. Over-abstraction leads to subsidence of the ground and leads to potential property damage in the region. And IGME, the Spanish Geological Survey, and DARES, a Spanish startup, are supplying maps to CHS, which are monitoring the movement. This enables the River Basin Authority to know when they should stop abstraction because it's causing potential damage. It's reached a level where it's causing potential damage to houses. It reduces the cost of in situ sensors, which need to be placed at the wellheads that you can see here. And it's leading to better regulation because knowing that the precise measurements can be made, the regulations can be approved, and the time limit of regulations can be improved, as can the thresholds be made. At the bottom, you see a pictorial which is our way of capturing these values. So for the economic benefit, it's linked to the dots down the side of each icon represent the contribution in that dimension of value. So the economic contribution is high, 32 to 70 million euro per annum. The environmental contribution is assessed at a level of 2, the innovation potential at 2, the regulatory contribution at 3, science and technology at 2, and societal value at 1. Now, I've taken out the part where I explain the basis for that, but that's something that I can explain in a report, or we have material on that, on the how those contributions are assessed. Next slide, please. So one of the earlier cases we did about infrastructure monitoring in the Netherlands, where gas pipelines and water pipelines are vulnerable due to movement of the ground. And what's happening here is that the houses, the infrastructure is anchored by deep piles, whereas the surface is moving due to subsidence and causing stresses to build up in the pipelines. So SkyGeo generate INSAR maps, which are supplied to the pipeline operators, in this case Stedin and Oasen, where they can identify the risks, plan their maintenance accordingly. This allows them to use their resources better. It leads to less risk to consumers from gas leaks or disruption to transport from major water leaks. And the local authorities can also plan better in the longer term development of areas. Here we were focused on the economic benefits, where the current benefit was assessed at being between 6.5 and 8 million euro per annum, but with a full potential of 15 to 18 million, largely by rolling out across the country and by improving the knowledge of history. Next slide, please. Now, one of the key facets of this case is that Sentinel data is very useful, but it's not the whole story. So on the left-hand side, you have a Sentinel image with the green dots, as you now know, I think everybody's familiar, showing stable situation. This is great. This enables to identify where there are problems, but it's not necessarily fine enough resolution to deal with all the issues that the water pipeline, the pipeline operators are working with. So then they're using the Sentinel data to trigger the purchase of commercial data, which gives higher resolution on the ground. So you can see that in the second picture of the houses, and indeed on the right-hand side where the pipeline is running under the road, and you can see signs of problems in there. So this is where the free and open Sentinel data is triggering commercial activity through the purchase of higher resolution data. Next slide, please. So now I come back to Norway. Here we're working with John, who spoke earlier, and Dag Anders in the Norwegian Space Agency. And we focused on looking at the impact of INSAR Norway on the roads sector and the management by NPRA, the Norwegian Roads Authority, to support the construction and management of roads. We'll come back to this tunnel that you can see on the right in a minute, but through the use of INSAR Norway, it's possible to identify where large-scale movement is occurring due to ancient glacial moraines or other geological instabilities. It enables to predict, to see where problems might arise, and therefore to go through better design processes. And it can also help resolve liabilities where construction works may have led to damage to nearby buildings. And I'll come back to each of those in a minute. And again, the pictorial at the bottom shows a 4 to 9 million per annum benefit in the road sector, and the pictorial showing the low environmental benefits, because this is not really helping to monitor environmental issues, but having strong influence on innovation, on regulatory matters, in research, and to society as a whole. Next slide, please. So there are three particular facets to the case that I wanted to identify. We've heard about some of them earlier. So the use of of corner reflectors. John went into that into some detail for the monitoring of rock slides. Here it was used by an engineering company where a new bridge was to be built across the head of a fjord to avoid the road going, or the local population needing to go around the end of the fjord, where several avalanches had caused accidents, indeed one fatal accident. So the decision was taken to build the bridge. This involved laying ballast as well as the final element of the bridge. Corner reflectors were installed upon the ballast in order to monitor how fast it was settling. This enabled the monitoring to take place remotely without needing to send engineers out to the site, and it enabled very precise measurements to be taken of when the ballast had settled to the sufficient state that the rest of the construction could be finished. So the work could potentially start more quickly because the tolerances on the movement of the ballast have been reached. Next slide, please. The second case, again, has been mentioned and even illustrated earlier. This is the centre of Oslo, where major construction works are taking place around the Bjørvika centre. There's a mixture of old and new buildings. The older buildings are largely built on wooden piles, and the new construction is causing some damage to those existing buildings, or at least a threat. So the key message here is that it's not just a question of knowing where damage is occurring, but also when it occurs. And the graph at the bottom there is showing points, the change of movement with time at a single point on the ground. So it's able to look at the velocity as being talked about, and knowing when the movement has taken place can help resolve disputes between contractors or between regulators as to what's going on. The next slide, please. So the third use case in Norway, I think John mentioned Tonsberg as well earlier. A tunnel was built. You saw the mouth of it on the first slide. It had suffered cracks ever since it was being built, and repairs were taking place each year just to correct for the movement. They'd done engineering studies to look at why the cracking was occurred, but they'd failed to identify the cause. And INSAR enabled that cause to be identified. So the next slide, please. Here we've got on the left a wide area and then a zoom on the right. On the left, you can see the roads on the left-hand side, upper left, which lead into the tunnel, and the area of the town of Tonsberg on the right. And the zoom in shows where the tunnel is coming, is enter or entrance, exit from the tunnel. And what's happening here is that the town has been built on a glacial moraine, which is sliding down into the fjord, and the tunnel happens to be right at the edge of that, so it's suffering the cracks. And here the message is that only through the use of INSAR can you look at wide areas and see what's going on, understand what's happening. Had this been available before, at the time of the construction of the tunnel, then different construction techniques would probably have been used in order to mitigate the risk of the damage. So the next slide, please. Excuse me, last couple of slides. So what we find from this is that INSAR provides the only effective means to measure vertical ground movement at a reasonable price and high precision and over a wide area. And that means different things in different situations, as I've attempted to show. What we're also seeing is many new applications are emerging. We've seen about some of those today, and predictions of where different sectors can benefit from using EGMS. One thing that has been alluded to, less said, is that as EGMS and national ground movement services build up a backlog and archive of data, this is going to provide a really valuable resource for future works in order to understand where damage could occur and what the risk of damage is. And the key message from the study is that it's not just about economic benefits, but there are strong social benefits, as well as improving regulation and in the other dimensions of the value. Then my last slide, please. And then just looking at it from a commercial point of view, I think the studies show that INSAR is becoming a really crucial technology for many applications. It has very strong commercial promise, but frankly, there's very limited market penetration so far. So this is a very, very interesting area to be working in. EGMES, we've supported. We believe it can trigger the use of commercial services for more frequent measurements with Sentinel. So Sentinel can provide more frequent measurements, or more precise measurements can be provided through a commercial operation. Many commercial operators, we've heard from some, are now offering INSAR services and are offering their services for EGMS and other users. But we hope that it's not just about supporting EGMS and local markets. We also believe this can help trigger large export opportunities, building upon the EGMS as a reference product supplied by such commercial companies. So that's, we're always looking for further SEBS cases. As I said, it has to be a Sentinel, use of Sentinel data. It has to have a primary user who is really committed to the project, and where the data, the use of the data has been embedded in their operations. But if you have further cases that you think we could look at, we're always happy to hear of them. Thank you very much.
Thank you, Jeff. Thank you. It's always interesting to see also the service from a different point of view. So with this, we finish with all the presentations for the workshop. Now I will invite Henrik to come. He is the master of the questions, so he followed all your questions during these presentations. So Henrik, it's up to you to tell us what is on the question side.
Thank you, Ivan, and thanks a lot for all the excellent presentations. I have to say, it's really good to see how these data are being used at national level and also by downstream services. We have a number of technical questions still, but I think I would like to start with a more general one. To begin with, there's a question concerning how national ground motion services should change to adapt to EGMS products. I think actually, in fact, Jeff was commenting on that to a certain extent before, but I would like to combine this question with some of the statements that we tested yesterday concerning if EGMS will foster general uptake and use of satellite ground motion data and products in Europe, and also the one about EGMS will facilitate development of downstream applications. I mean, these are very general questions. We got a very positive feedback yesterday, but in fact, I think I would like the speakers to comment on these things. So first of all, I mean, in what way do you expect that you will need to adapt to a future European ground motion service? Do you agree that a service like that will actually foster uptake of ground motion products in the future? And also, can you see that actually you will also be able to develop downstream application based on these products? And I think actually I would allow all the speakers to comment on that. And I think that we could start with Svein, actually, if you would like to provide a comment.
Hi. I guess for us, it's always interesting to have as many data sources as possible. So we would definitely be looking into this and using this to produce services in the future as well. I think that's basically what I like to comment on.
Okay, thanks, Svein. And I'm going from the bottom up. So Sebastian, would you like to comment?
Yes, of course. I think this has been basically the main message of my presentation. Is really we're really looking forward to the ground motion service, to the European ground motion service, because we strongly believe there we can add on value on that service towards the really user requirements. we can add value with commercial Zoom service based on commercial data. And of course, as has been mentioned by Jeff, as we are providing as well core service type of services already, we intend to export that European ground motion service to other parts of the world. And so now we can show the example, we can show what we are aiming for. And this is a quite interesting, let's say, more mature business perspective in the INSAR domain as we ever had.
Thanks, Sebastian. And I will move on. Michaela Frey, would you like to comment as well?
Yes, thanks, Henrik. Yes, I think we need to go forward on this point. If we have a European-wide INSAR database and INSAR and the service connected to the land service, of course we will adapt the national ground motion service, and I think specifically in a way that we have then resources to go for specific user needs. As in Germany, we are quite often asked to have a more frequent update of the data, especially for areas where we have strong incidents of movements related to different themes. But we are facing this, and so we are looking forward to the European Ground Motion Service also in a way that we have a space to have quarterly or half years update of our project, maybe also only for specific areas. And on the other hand, we will adapt and see also to meet our user requirements on national level regarding referencing to geodetic data. So there is also an open discussion, and a discussion we already started in this way. So yeah, so of course we will adapt, and we have to adapt.
Thanks a lot, Michaela. And I will move on to Luca. Would you like to comment?
Yes. Yeah. Yes, I can say that national ground motion services have specific goals that are obviously different from pan-European products and also regional services. So it's different. If we understand very well the goal, the target of each of these services, we of course have we don't need to change. We just, because automatically it's something that is calibrated because it's a different target. Of course, we must maintain the coherence in order to have results that are not conflictual.
Thank you very much. And then John.
Thanks, Henrik. I tried to outline in my presentation what our plans are. We're quite confident that we don't know yet who will be providing data for the European Ground Motion Service, but we're quite confident that EEA, with their tendering system, will be able to supply us with ground motion data at least as good as what we're producing now on a yearly basis. So we think that this will allow us to shift our focus and spare us some resources that we can devote to more frequent updates in certain key areas in our for our national users. So I think it'll be very complementary to us. At the same time, of course, we will continue, as I said, to work with new tools and try to look forward to new data sets like NISAR and ROSE-L, which of course might in the future work their way into EGMS as well.
Thanks, John. And Jeff, would you like to add? I mean, you have already provided some of the answers, but if you would like to add a comment.
Yes, thank you. Yeah, I think I did cover a number of the situations in my presentation, but I think we see that EGMS will be an annual update. So the potential for providing more regular data and to stimulate more regular data. We see a number of services coming out of this. We've seen examples of portals being set up where users can just go and pull out most recent data. So I think there will be a strong stimulation, whether it's for more regular measurements, whether it's for more precise measurements in terms of spatial resolution on the ground, or whether it's for new applications, because I think there are still many new applications that are still to be developed here, and there's a lot of innovation taking place. Thanks.
Thank you, Jeff. Federico?
Well, nothing to add, but the confirmation that the scale of these different services are different. So there is an overlap, of course, but considering the scale of application, also the products are different from regional to national to continental scale. So that's more or less the point. Different scales and different application, also mainly in terms of frequency of updating.
Thanks a lot. Eleftheria, would you like to comment? Okay, so we can go to André. Would you like to comment?
No, I think the main points have already been mentioned. So it's a matter of scale and different processes, and different update frequencies, for example, and also application driven products. So yeah, I think it's a development, and it will be most likely complementary.
Okay, thanks a lot. And I could see Eleftheria. Would you like to comment?
Hello. No, I'm already covered. Thank you.
Thanks a lot. Okay, and I think then I will move to some specific questions related to the last presentation. So there is one, actually the very last one to Swine. What image did you use to calculate the deformation of the buildings? So that's one is for Swine. So please, Swine.
Yeah. Well, we used calculations provided by Norut, now Norse, and we used those data in combination with cadastre data that we have combined. So that's where we found our information. So if you need anything more specifics, of course, don't hesitate to contact us.
Okay, thanks a lot. And there is one specifically for Jeff. I can see about aquifer monitoring. How do you ensure to get enough points? Sorry.
Yeah,
I lost it. Yeah,
enough permanent scatterers, I think. Yeah, it's deceptive. Of course, they're rural areas, but we're also looking at the impact on infrastructure, on housing. So around the housing, there's built up and permanent scatterers that are appearing. So there is it's deceptive, and of course, it's looking at an area around the well's head, or the multiple wells, because it may be the whole underground aquifer that's being monitored. So I hope that answers the question.
Okay, thanks for that, Jeff. I just lost the question. I couldn't. It's moving up and down here on my screen. Sorry for that. No, I said moving to the top again. I can see that the topmost one is rather a statement. So it's a statement concerning some important work done by CR in ERA in Italy, where they have actually produced a pan-European wide product, and there's a very nice article available, and you can find more information there. So the next question, and I don't know if John, for example, would like to comment. Are there studies for optimal length of archive treatment? Would that be one for you, John?
Well, I can try to take it. I think in this case for EGMS, the biggest question here will be how much data do you use during updates, frequencies, and of course this is probably covered in your tender. The question is, of course, how much there's a trade-off. The longer data you have, the longer, more interesting time series you have for a given object, but that object has to have existed during the time that you're analyzing. So if we want to cover deformation in new buildings, we need to have a shorter time series. On the other hand, with the shorter time series, you can't have such a good estimation of the velocity. So it's a bit of a trade-off. So we have to come up with a period of time that would be useful for analyzing data. And I think probably 4 to 5 years is a good compromise.
Okay, thanks for that, John. I think we can probably take a few more questions before we stop. Then the next one is about workshop or about best practices to deploy networks of corner reflectors. And the one after that is it would be useful that corner reflectors installation could be coordinated with URF. I don't know if you, Eleftheria, would like to comment on this one.
Hello. Yes. I think it should be coordinated. Yes, because we must put the reflectors in places that we know that are stable on one hand, and some in places that are moving, so we can have the related movement.
And the question concerning best practices, is that something they can find on your website or?
No, not on our website. I think the people that have their national services are best to answer, because we have the knowledge of the geology and the geohazards, but we don't have a network of reflectors. So maybe John or somebody else from Norway or Germany that have these networks could answer best.
Okay.
Better.
Yeah, okay. So let's, Andre, would you like to comment?
Yes, as I said, we are working with the geodetic agencies in Germany for that reason. And yeah, there's also a working group of the geodetic agencies regarding INSA, where this topic is discussed regularly. Yeah, so this is a national thing with respect to the Ground Motion Service Germany.
Okay, and John, maybe you would like also to say something?
Well, there are two. They mentioned two questions in the two aspects in the question. Of course, local corner reflectors for validation, and then something to do with the reference state of connection. I think that in EGMS there is, of course, a requirement to produce eventually a harmonized a product that is harmonized with GNSS, and they will work together with GNSS community to do this. And this is planned, but so I don't think the workshops are very relevant in that case. But for validation, certainly we could share our experience on doing local validation for local deformation phenomena.
Okay, thanks, John. Federico, Luca, would you like to add something?
Well, it's Federico speaking. No, I don't have any additional information that I don't think I'm the proper person to reply to this answer, because yes, we have a small experience in installation of some corner reflectors just to increase locally the density of information, but we are at a very preliminary stage for this activity, so I have nothing to add. Thank you.
Okay.
Henrik, may I just give a comment on that?
Of course.
I would like to point out that in the course of the task force work, we released a questionnaire to all the members and beyond, also to the geodetic surveys, etc. And one point which was I would like to stress out of this feedback of the questionnaire, that we have a lot of different corners in Europe, which were, set up for different purposes and applications. And I think it would be really important to have a kind of a workshop, meetings to discuss standards for corner reflectors if we are planning, and also for the future, to be used in the EGMS. As to the fact that what Eleftheria also said, some of these corners are not set for, for EGMS information base. Some others are in private hands. We do not have, we can't use this information for the EGMS, etc. So I think it would be quite important also to get this done and to harmonize information that we really can properly use it in the EGMS framework.
Thanks, Michaela. And
just to complete, this is Luca. Just to complete this to answer, I have to say that in Italy we are the need of GNSS data to calibrate, validate is important. Is a milestone for very important, very relevant for regional geographical surveys. They always have mentioned this is a primary goal, and also regions have their own regional geodetic networks. So in this sense, the idea is to put together this and try to organize in a suitable way this effort at the national level. Then I don't know what can be done, of course, at the European level.
Okay, thanks for that answer as well. Ivan, I don't know, do we have more time?
Well, we are already out of time, Henrik, but I think we can take probably a few more questions, let's say 4 or 5 minutes more.
Okay. Then I will try to answer 2 questions specifically concerning ETMS. One is about the update frequency. We are planning annual updates, and it will probably not change for the years to come. If you want more frequent updates, probably this will be for national ground motion services or for ground seam applications to meet these requirements. And concerning data policy, yes, all these data will be available according to the Copernicus data policy. Therefore, they will be openly available. Okay, so there's a very specific question to Andre and Federico. Which software has been used to process Sentinel-1 images and obtain velocity measurements? So, Andre, would you like to start?
Yes, of course. As I said in the presentation, German Aerospace Center was contracted for the processing, and it was their PSI wide area processor, which has been used.
Thank you. Federico?
Regarding the regional processing, the software used is Squeezer. And regarding the national Sentinel-1 coverage is SBAS, a small baseline subset from CNR IREA.
Thanks for that answer. And there's one specifically for John. What is the method used to generate the velocities of the measurement points?
Essentially, it's the same question. Yes, we use a standard persistent scatterers approach, a PSI approach. We use software that's been developed by Norse in Norway with help from BBO Labs. This is software that's developed actually over the last 15 years in Norway for our usage.
Thank you. And in fact, the very last one I can see, which has not been answered yet, as far as I can tell, this is for André. What is the maximum velocity measured in the mining area close to Cologne? It's maybe a very specific question. I don't know if it's possible for you to provide an answer.
It's about 5 centimeters per year in line of sight.
Thank you for that. And Ivan, I think that's it for now.
Okay, thank you, Henrik. So I think with this, we came to the end of the workshop itself. So during the 2 days, we presented the background for the service, the planning, the different products. We presented also some use cases and applications at national level and also in some specific uses. So I think this was really, I hope it was really useful for all of you. So we have seen quite an interest via the high number of questions. So I can guess that it was very useful. Mind that the presentations and the recordings of the event will be available offline. So if you want to check again something, or if you miss some part, or if you want to share with colleagues, don't hesitate. This will be available, so you have the possibility to see it offline. So with this, I would like to thank all speakers for their presentations, to thank all the people in EAA and also in the European Commission who made this workshop possible, who worked a lot on the organization. I want to thank also particularly MCI, which were in the background for technical support of this event. And of course, thank also all the participants for connecting and participating. So you made this workshop useful and interesting. So thanks to everyone, to speakers, organizers, and participants. So for me, that's all. I don't know, Henrik, if you want to say a few final words before we close the event.
I would just like to thank all speakers as well and all participants, of course. And I just want to wish you to have a nice day. And I hope very soon to be able to inform you about a more exact planning, so you know when to expect this new exciting product, or when you can expect it and when you can use it. So we are looking forward to that. We are looking forward to delivering this product to you, and we are looking forward to your feedback. So thanks a lot. It's been very interesting to hear all your presentations.
Okay, thank you very much. So this will be not the last time we will talk probably, so you'll still have the possibility to talk on this subject, and in the future it will be more and more active. So thank you very much, and have a nice day, and hope to hear from you soon on any point. Thank you. Bye.